5, and 6, you're asking yourself two questions. Did we get the right answers? And that is contingent. Step 5 is contingent on step 6. Did we ask the right questions? Did we get the right answers, and did we ask the right questions? These are really important. We had a student a couple of years ago attempt a very complex finite element model. It was a tube with a load on the end, and the student never pinned it down from moving in space. So he could never figure out why his computer kept crashing. Well, the problem is he didn't have the right model created. The other aspect of that was he had a tube that was pinned on one end and a load on the other end that looks like a cantilever beam to me. Instead of running a finite element model, he could have just done this in 32 seconds with Euler-Bernoulli beam theory and sort of minimized his level of frustration. Right? So are we developing a model to answer certain questions? And once we get those questions answered, are the answers right? So don't underestimate the model, checking a model with just simple hand calculations. I spoke about this. So in terms of finite element, I don't know how many folks have experience with finite element. It is quite complex and can be quite complex. I'm going to simplify this down into a series of steps. There's a mishmash of numbers and letters here. I put step 0 in because in order to create or do step A, you actually need to have geometry. This is what it implies. But basically, the finite element modeling process, we allow basically an auto mesher now to divide a solid continuum geometry into smaller and smaller elements. And each of those elements is called an element. They create a mesh. Those elements have nodes and edges associated with them. And each of those elements in step B actually is assigned some sort of governing model. Okay? So that governing model is going to be contingent on what sort of behavior we're looking for. So we can simulate temperature, we can simulate displacement, we can simulate magnetic field, we can simulate a number of aspects, and so we have these small scale approximate models. We take our small scale approximate models and our number of elements, and basically within finite element application, we're solving just a series of matrices. Large numbers of matrices. This is why as your model size gets bigger, it takes longer to solve, because essentially you're doing a matrix inversion process. So steps C and D are sort of behind the scenes. Step E is when you hit the solve button, and then step A is where it generates these beautiful pictures. If you're keeping notes, you should put a star next to step F. People are enamored with beautiful pictures. Sometimes those beautiful pictures don't make any physical sense. But man, if you can throw a beautiful picture of a contour plot of a displacement on a PowerPoint presentation that you might have due in just a few short weeks and it doesn't make any sense, that's a problem, right? So when you display those beautiful pictures, you have to actually figure out whether the results make any sense. Okay. A few comments and then we'll shift over to ANSYS. Finite elements are rarely exact. Okay, it will give us good results, but not exact results. And so this is important. There is some assumptions within a finite element program that limits it. And this is true. Finite elements can make a good engineer better, but it can make a poor engineer dangerous. How many of you guys have ever used, say, the finite element of the simulation capability within SolidWorks? By show of hands. Anybody use the simulation capability within SolidWorks, or by screaming, or maybe screaming is not great. I have seen students do that and they had no idea what they were doing, but man, it created some beautiful pictures. So let me jump ahead here and show you some examples within the ANSYS program. So let me stop sharing my screen. Let me stop sharing my screen. Stop. How do I stop share? Okay. And let me come over here to another computer. For those of you with a Mac, this is just, this tells you basically that Macs are no good. by the way, because I have to use a different computer. So can everyone now hear me and see me on a different computer? See my screen? Okay, good. So this is an example of ANSYS. Let me back out of here. Oh boy, I didn't mean to do that. So here's an example of ANSYS Workbench. I was trained on the APDL, so the ugly side of ANSYS, but it turns out Workbench works really well. On the left side, what you can see is a series of different types of analysis. So we've got something that comes down here to static structural. If you're doing that, the UAV that flies over fire, you might look at like a transient thermal or a steady state thermal. There are some advanced types of analysis that can be performed. There is a combined CFD and static structural analysis, okay? But here are some examples of some analyses that you can do. And essentially what Workbench allows us to do is to drag these analyses over onto this palette, okay? So just show you a real quick example. I want to do a static structural. I'm going to drag this static structural. Oh, I can't do it here. Let me get rid of one. Let me get rid of this one. Okay. I'm going to drag this static structural over onto this palette, and you guys should all be able to see that. So this little block right here is the analysis that I'm doing, and I'll just name this as a spar analysis. Okay. So when I start to run this spar analysis, this ANSYS Workbench, or ANSYS in general, it does have a geometric modeler, but it's quite terrible, so I don't advise that you use this. But the first thing I need to do is start with engineering data. Okay, so within engineering data, you guys can see this. This pulls up a bunch of data sources. This is essentially all of my material properties. So I can open up several material properties here. I've got libraries of different materials. So I've got general materials all the way down to composite materials. Likely what you're going to, your eyes are certainly got big probably right now. You're going to be composite materials. This is fantastic. I want composite materials. So you could use some composite materials. I would advise you not doing that at this point just for demonstration, because likely these materials and material properties do not and are not similar to the types of material properties that you'll have within your system. So I can bring this guy up here. I can try to edit this, open this up. Should bring me up an editable version of this. Where is it? Didn't bring up an editable version. Okay, well, I don't know why this, Murphy's Law. But what I have access to here is a bunch of materials. So I'm just going to go to general materials. And I know this is probably not the material of choice, but I'm going to choose an aluminum alloy. If you see this little plus button right here, when I add that plus button, I'm adding it to a simulation that I would like to run. So I can add aluminum alloy. Again, I'll add some titanium alloy. I'll add structural steel. Okay, so those are the materials that are going to be available for me when I run a simulation. And I'm going to explain some additional things here in a second. So now I've got those materials. I now want to bring in geometry. Okay, I'm going to right-click on geometry and import some geometry. Now, we at Clemson did not buy any translators, so it doesn't take native files very well. Tyler Stapleton talked about all of the different types of formats that 3D Experience has. I tend to be a user of STEP, so I'm going to browse for a STEP file. It should be noted that I created this STEP file from SolidWorks in this case. You could create it from any number of CAD applications, but we would encourage you to use 3D Experience. What you see now after I imported that is a check mark. That means that I have geometry associated with this model. I'm going to double click on that because the geometry is associated with it but not updated at this point. The magic of computers is a little bit slow, so I will pause at this point. Are there any questions on what I did here with ANSYS Workbench? Okay. Well, you see nothing Okay, the geometry is apparently there, but you see nothing. So what I need to do is generate some geometry. So there's a little button up here in the upper left-hand side. Generate this geometry. And now what we have here is a body. This body is made up of the motor mount. It's a dumb blob of material. Yes, if you look at this, you can sort of see some lines, but it assumes that this body is just one big solid part. You, as a group, may decide that you're going to make this by gluing together 4 different parts, okay? But when I exported it from SolidWorks into a step file, it now is just one solid part. So I've got that part. I can look at some elements or details about that body, but essentially what I have now is the geometry. So I've got that step 0. I've got the geometry. I'm going to close this modeler out. A couple more minutes on this, guys, and I'm going to model it now. So I open up the model. You see this sort of these 2 arrows going around. This means I need to do something. And now what it's going to do is pull in that geometry into my model. And so here it is. So I've got a geometry. Reference temperature, I can change these sorts of things. What I'm predominantly interested in this motor mount is going to be changing the material. I want to change the material to something really great. We'll do it as titanium alloy because it's exotic. So now this is going to be titanium alloy. If I had more than one geometry in here, I could specify each body could have a different type of material. Okay, so we have the geometry, we have a material, we need to mesh it, and so I can just go ahead and generate a mesh. So there we've got a mesh. I can insert some refinement. I can change the mesh size. I can begin to look at a mesh. One thing I don't like about this mesh, and this comes from experience, maybe it's too coarse, right? So I can actually come back here to sizing of the mesh and put in and change to a fine mesh, okay? I'm going to have to remesh this, update this mesh. So now it's going to update, and you see here I've got some additional elements. The element size has gone down. Now what I've got here is I've got the mesh. I need to apply some boundary conditions. So I came here to static structural, apply some boundary conditions. I right-click that, insert, and I'm going to put on some boundary conditions. So I'm going to do a fixed support here. That fixed support, I still am on rotation. Certainly the interface is a little bit clunky with ANSYS. I need to come up here and I want to assign this fixed support to a face. Select that face and apply. So that fixed support is now on that face. What I'm going to do now is put on another load. I'm going to put on a force. I want to pick this face, apply that, okay? And I can apply that along that face. So now what I currently have is a magnitude of 0 with a vector. By creature of habit, I like to specify components. So now I can begin to specify the components here. So let's see. I may put on this, say, a Y component of, I don't know, 0.25 of a pound. This may be the mass of your motor. I might then put an X component on here that is going to be, say, a thrust. So I'll throw 15 pounds at it. In this case, it's pulling out. So maybe it's best that I make a negative 15 pounds. So now it's going to go the other way. All right, so now I have specified the weight of the motor here on and then the thrust of that motor. Come down here to solution and right-click it, insert a stress tool or a deformation. So I'm going to look at maybe putting in a directional deformation plot. And I want to put in how this deforms along in the z-axis. And maybe I want to put in sort of a total stress, equivalent or a von Mises stress. Okay, so that's it now. So I've set my geometry and materials. I've meshed it. I've added some boundary and loading conditions. And now what I can do is solve. Okay, so it's solved. There's no pretty plots just yet, but I can begin to look at sort of what's going on. That may be alarming. You might go, holy cow, 15 pounds from the motor is going to displace titanium by a lot. If you actually begin to look at it, this is just magnified for the purposes of visualization, and so I can actually change this. I can change the magnification factor here, right? So this is at maximum. We've got a displacement of 4.6591 times 10 to the minus first inches. Look at equivalent stress. We're well below the equivalent stress. Okay, does that make sense to everybody so far? Any questions? Is everybody still there? Am I talking to nobody?
We're here.
We're here, and it makes sense.
Okay.
Makes sense.
Now this is a pretty simple problem, guys, but it gives you sort of the basics of at least using ANSYS. I would suggest, and I'll offer this up in the past, when teams had specific problems, the best thing to do would be to contact me and set up a time outside of this, and then I'll give you some fair warnings. A fair warning is this: you don't need to simulate your entire plane, okay? So if you're interested in sort of the strength or deflection of the spars in the wings, you don't necessarily need to model everything. You don't need to model all of the foam and all of the fiberglass. You would model the spar. Now this would be a limit, right? But you would say, the carbon fiber spar is the thing that is predominantly supporting the load, so we'll just model the carbon fiber spar. Things like assemblies begin to get really, really, really tricky. We had a student a couple years ago trying to simulate their plane, but the assembly went sort of crazy and was never able to actually solve it. So these are types of things that you should think about. I'll show you a few more things here. Let's suppose I wanted to do a slightly different analysis, okay? And I say, oh, this is spar analyses here, but actually this is not spar analysis. This is motor mount. And this is going to be thrust. Okay. Well, if I want to do maybe a similar analysis, but I want to use different loads, I could come in here, and I could do this a couple different ways. I could do a static structural again, okay, and I'm going to drag this over here, okay, and this is going to be motor mount, I don't know, thermal. No, this is going to be motor mount for a moment, okay. Now, I can actually share information, so I can come over here on this one that I've already created, engineering data, and drag it over here. So you see there's a link there now. I can come over here between geometry and drag it over here. Okay, so now I'm sharing the geometry between these two analyses. I could then come in here to model and create some different models. So maybe I want to share the geometry and the data, but I want to create a new model. So I can actually specify a new model at this point. And I'm going to go through this whole modeling process again, right? So maybe I want to create a different sort of simulation model in here. I'm okay with the mesh, but I want to create some different loads. I want to use moments here instead. And so you can link data between the two. The other thing that you might be interested in doing, and we can talk about this offline, is a sort of design exploration or optimization type approach. So we talked about trade studies or parameter correlations or response surfaces. We can drag this in here and get a response surface. And so let's suppose that I wanted to change the load on here. I could use this as an optimization parameter to do a trade study here on how the load change would ultimately change, say, result in a change in thickness of our motor mount. And so we could give it different loads and explore how a change in thickness of the motor mount would change sort of stress and that type of stuff. So that's a real basic element of ANSYS. I did want to bring up a few other things, and hopefully you can still see me on this. Can everybody see my web browser now?
Yes.
Okay. So I went to a couple of carbon fiber manufacturing or suppliers, and I'll give a couple of examples. If you guys do carbon fiber spars, carbon fiber doesn't behave like metals. And so understanding sort of what tensile modulus means, you need to look this up. Carbon fiber is typically directional, okay? This is the tensile modulus of the carbon fiber, the fibers itself, but you mix carbon fibers in with epoxies to make carbon fiber reinforced polymer epoxies. You'll see has a lesser of a tensile modulus, okay? And so you need to look at these sorts of things so that you know what material properties to put into your simulation. The other thing you need to look at is going to be fits and finishes. So here's from another supplier, Rock West. There's some tolerances associated with here. Okay, so if I go to Rock West Composites and pull up their tolerance sheet, it begins to tell me what sorts of tolerances are held within their tubes. Okay, so if we look at like a rolled tube, it can be plus or minus 0.006 inches between these diameter ranges. Okay, so you should think about this when you're starting to assemble these together. Okay, and then here's some length tolerances. So look at under 48 inches can be plus or minus 1/8 of an inch. That's quite long or a big tolerance, right? So these are things that you should be aware of. So with that, I'm actually thinking I'm over time by a little bit. Are there any questions? No, okay, great. I've got a couple of examples and a couple of videos. I will post them up. They're not lecture videos. They're just walking through example videos. So I will post those up to the folder on the lab material site. Okay? All right, I'm going to pass the torch. Thanks for paying attention, I think. Carl, you have anything, or are you ready for us to get going?
I think we're just going to have Dr. Bowen start.
Oh.
Okay, can you see? You see the screen all right with VN diagrams?
Yeah, we can see it.
Great. What's a VN diagram? Well, it's really the envelope that you can fly your airplane in without stalling and without breaking it, and relates the airspeeds to the maximum expected structural loads. For regular aircraft, there are sets of FAA guidelines or requirements for the VN diagram of the flight envelope. So we need to make some assumptions and have data for our aircraft available to form it. We will form an initial maneuver envelope with the design speeds for your aircraft, and then we'll complete the VN diagram with a gust envelope. So start with just maneuvers, takeoff, landing, maximum turns, maximum pull-ups, and then we'll add flying through gusts, which is important for commercial aircraft, may provide some of the highest loads, getting in a storm or getting into clear turbulence. For us, we'll bounce around a bit, and probably the turns and pull-ups, particularly during your launch period, may set your upper limits. So first of all, aircraft under load or at rest is under load factor of 1. So what's the load factor? The load factor is the number of G's that you're pulling. So N is equal to the load over the weight of the aircraft. So the VN diagram exists for various aircraft configurations and flight conditions. So the manufacturer will have to satisfy the FAA requirements for clean aircraft takeoff and landing. They'll have to go through the whole range of from minimum flight weight up to maximum flight. They'll have to consider, we'll just look at the subsonic version. Of course, they'll have to consider the transonic versions for commercial aircraft, supersonic versions for military aircraft. We're just going to look today at the clean configuration, flaps and landing gear retracted, and maximum takeoff weight for the aircraft. Let's take a look at the initial maneuver envelope with the design speeds. This is a basic VN diagram. We'll talk about how to construct it here in just a little bit, but this is what it looks like. We're plotting the load factor N versus velocity. As we increase speed, angle of attack, we get into regions where we're going to stall the aircraft. We can get up to a load, a maximum Q load. This is maximum dynamic pressure. We get to the VD. This is a dive speed. It's not the death speed, but that's appropriate also for that. And on the negative side, we have the same thing. Typically, we don't pull as high loads on the negative lift as we do positive lift, but we were down watching the air races in Indianapolis 500 track, the Red Bull air races, and they pull as many negative G's as the positive G's, and they are limited to 10 G's positive, and they have an accelerometer on board, radio link to the officials, and a number of the airplanes went over 10 G's in their pull-up maneuvers, and then they pull lots of negative G's too. So we're not going to pull that many G's. I hope we won't do that. So just said the axis, the load factor versus an equivalent airspeed. For us, we'll be flying low enough so that our flight density is equal to sea level density. So the equivalent airspeed will be equal to our actual airspeed. We have the limit load factor, which we designed to, but we've got to add some safety factor to that. Typical number is to 1.5 times the limit load factor. So we'll design this ultimate load factor so we don't, we have some safety factor, which is usually 50%. So we have to determine what the positive limit load factor and plus, and the negative load factor and minus. For our aircraft, we'll have to make some judgment on this. Typically for small UAS, we might design for at least a 3G load. We'll certainly do the basic load test by picking your airplane up by the wingtips. That's equivalent to a 2G load, or about equivalent to a 2G load of a wing with a elliptical load. You can expect to get over 3G loads sometimes, particularly on launch, as I said, or sometimes you get into some violent maneuver, or we get out, we're flying on the sort of the wind limit where we want to fly at, but it's the only day we have to fly, and you'll start picking up some heavy loads at that time too. So you'll have to determine what it is you want to do and what effect that has on the weight of your airplane and therefore the performance of your aircraft also. We could construct all the lines on the VN diagram, the stall lines. Stall is just comes about from the definition of lift coefficient. And so instead of just the weight, though, we have n times the weight. So n times the weight is a half OB squared, dynamic pressure times the area times CL max. So this is CL max on the plus side. So this gives us a parabolic line with respect to the velocity. And then negative stall, typically with the airfoils you're looking at, you won't be able to get as high negative lift as you can get positive lift, so your wings will somewhere. So this just shows a typical CL versus alpha curve. We get a higher CL on the plus side than we do. So this is beginning to put our VN diagram together. And then what's our cruising speed? You're going to decide that based on the requirements for your particular mission, and we'll just have a vertical cruise speed here for commercial aircraft. It's really related to sometimes to the gust loading that we can have. Then there's the structural maximum dive speed. This is determined typically with aircraft, and it could be for yours too, by flutter speed of your wing. We have some pretty flexible structures sometimes. Sometimes we have carbon fiber foam wings that are very, very rigid. Other times the balsa mylar is not so rigid, and we can get into flutter problems at high speed. So coming down, you'll flutter and break the wing. So we need to take a look at that. But typically, you want to design for about 40% above your cruise speed. The VNE, velocity you might see, is what they call placard speed. So every aircraft has a placard on the control area that says this is the maximum you can. The design maneuvering speeds are the intersection of the maximum load speed and the stall line here. You have a design maneuvering speed plus side, and also design maneuvering speed negative side. Military aircraft in a dogfight will be up in this area here, near stall because they're pulling a lot of lift coefficient in high G turns, and so that puts them up in this part of the envelope where they're near stall when they're breaking the airplane. We put a couple of lines here at 1G, so this is no loads. Then we can sort of begin to connect all the dots and erase all the lines, and that gives us then here to here, 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 back again, gives us the initial VN diagram without the gust. And then we're going to complete the VN diagram with a gust envelope. And so turns out that for commercial aircraft, if you've been on a commercial aircraft in a storm, where the coffee has hit the ceiling of the aircraft because you've hit some pretty strong gusts, pretty strong turbulence, then you know this is an area that really stresses the aircraft. So we have a wing here at some nominal flight condition, and we get plus and minus gusts for Part 23 aircraft, smaller aircraft, has to withstand plus and minus 50 feet per second at the cruise design, and 25 feet per second at the maximum dive speed. So won't go into these, but experimentally, with some analysis, load parameters have been defined so that we have some sort of a gust load factor as a function of airspeed. It will be a linear function of airspeed. There's a number of these out. There's ones that are specified by the FAA or by the European agencies also. So this then comes out to be linear lines that start at n equals 1, and there's a 50 foot per second, 25 foot per second, plus and minus. And so these begin to define other limits on the loads that you can have. So we can calculate the intersections of BC and BT with the loads, and these will then decide whether we're being limited by the gust load or whether we're being limited by the dive speed or a maximum load factor. So we put that all together, and we get a gust VN diagram, or the gust loads attached to the VN diagrams, and we can see the gust loads have some. So load factors do represent the loads, but they've got to be multiplied by 1.5 yet to put in a safety factor. 1.5 is a lot for us. We may not need that for the small UAVs that we're talking about. So just another picture then. This is was a VN diagram from a project a few years ago. So this is now looking at an even smaller UAV than what you were doing, but it has all of the factors that looking at, so that turning flight here has a load factor of 3G, looked at a maximum Q load based on the structures. From the aerodynamics, have the stall speeds and for a plus and minus. And so this does not have any gusts on it. I don't know of any SUAS load factors with gusts on it. There's some for bigger UAVs. I mean, you start talking Global Hawk with a huge flexible wing that's got to get up through a lot of turbulent atmosphere. Once it gets to the heights of 60 or 70,000 feet, it's not a problem, although there could be some clear air turbulence up there. So this is what we're talking about. You've got to fly your airplane within this load. This is also the diagram that tells you what loads you're going to put in to the finite element analysis that Professor Mako just talked about. And these are the loads. And how do you get those loads? And how do you get their distributions? Well, the aerodynamic analysis, whichever one you choose to use, you could use X-Flyer. ABL will also give you the span-wise load distribution on your wing and on your tail surfaces. So that will tell you where you are within this, and then say, okay, I'm going to look at a condition here at the corner of near maximum G's and near the stall gun. And having said that, you can get the load distribution of either one of those aerodynamic analysis to begin looking at the structural analysis of your components. So, pick a couple of corner points to look at, and if you can satisfy those, you'll be okay. I've seen things break on the backside too, inadvertently. Somebody got upside down and collapsed their wings also. So I hope you don't do that. Initial flights, minimum weight, minimum battery, no payload. Get the weight down as low as you can, and that will begin to tell you what you can do. Then you begin loading your airplane up to the full conditions that you designed for. So that's the end diagrams. There is both the lecture and this spreadsheet are loaded up on SharePoint. This is a free spreadsheet that's available that helps you construct your VN diagram. It's in knots at the moment. Other people have gone and just changed that. If you want to go to feet per second or meters per second, it's relatively easy to do. You just have to put in a factor here. But you can go in and change the various corner speeds, and it'll redraw the VN diagram for you. So it's a fairly convenient way to go about getting a quick So, questions? You're going to need one of these. You need to know where your loads are. Can't do any structural analysis till you know what your loads are. So you need to be able to calculate that. I think the good news is we've got a bunch of ways to get the load distributions for your structural analysis. X-Flyer, has a bending moment versus span, load versus span. So it'll tell you what you need. Has anybody ever seen one of these before? Well, a couple people have been out on summer jobs and have seen these. I don't know. Georgia Tech people, have you looked at VN diagrams from some of your other design courses or work experiences?
So, yeah, the vehicle performance class, they all see VN diagrams. Whether or not they build them is a little different, but yeah.
Okay. And there's a little bit of a difference between doing it for commercial aircraft and small aircraft, but just in terms of scale. But it's relatively straightforward to do it, and it does give you the flight envelope, which is something you really want to see. Clemson, students have ever seen this or heard of it?
No, we've never seen this before.
Well,
So, in terms of the use here, we're determining our loads, right? So this ties directly into the stuff that Dr. Mako was talking about in terms of what is the load being seen on your wing. You could do a simple Euler-Bernoulli beam bending theory, but you have to come up with some loads, and this type of method can give you those loads.
Well, this type of method, for instance, for the wing or the beam, as Carl said, gives you the total load. And then you need the load distribution also. But as I said, one of the tests that's very commonly done for model airplanes, a small UAS, is to pick the airplane up by the wingtips. And that comes close to a 2G load for a elliptic wing. But I think you've got a couple tools that will give you that distribution that you could also put into the finite element analysis. And the integral of that distribution would give you the load that we see on the Venn diagram. Any other questions? Tuskegee, any questions on this?
We're good.
They're here. Okay. No questions, though. BYU? I don't know if you've seen this before. Is this something very common?
Yeah,
Thank you,
no, we're good.
Okay, you're good. All right. I think it's straightforward to construct, and it's, I think, a necessary part of what we're doing. Okay. Other questions, comments? Okay, that's all for me.
So Steve, if there isn't anything else in this lab, can I talk for a little bit on the hand launch? I've got a couple models and things I can show.
Sure.
Stop. Okay, so obviously the hand launch is an extremely important element of the design, and our previous constraint relationship, where we're kind of modeling it as a short takeoff, is not really the best approach. So one method would be to do a more simulation-based approach here. So in this case, it's a very simple Excel model I built in like half an hour, where the assumption is that you are flying at a constant CL. I label it CL max, but really, as soon as it comes out of the hand, it stays at a constant CL, and that's defining the lift force. And thrust is also constant, and that's defining your forward acceleration. And then construct a a set of first-order differential equations and integrate those over time. So your forward acceleration is just going to be equal to the thrust minus the drag divided by the mass. Your vertical acceleration is going to be the lift minus the weight divided by the mass. And lift is just based on 1/2 rho v squared s c sub l, where c sub l is equal to CL max. So in this case, this is a very dirt simple method. I use the simplest numerical integration possible with just the forward difference, which is also not great. And you get some level of simulation model, but it's at least a starting point. So I wasn't really satisfied with that. So the first step, the thrust is not really constant. We know that that's not true. We know there's a thrust decay with velocity. As you increase your velocity, your thrust goes down with our fixed pitch propellers. So I built a couple MotoCalc models for representative sizes. These are based on Hacker motors that we've used in the past, a Hacker 830, 30 millimeter can, 40 and 50, and those are different sizes. And the static thrust varies from 4 to 12.5 pounds here. And essentially, I put that into a model to get, or created a model to get the amount of electrical input power necessary to give a pound of thrust, and that stays relatively constant across the sizes of motors. And then a thrust decay at 30 miles an hour, so we're getting a linear thrust decay with forward velocity. So those are just some very simple curve fits in this case. The numerical integration is also not adequate, but fortunately, MATLAB is here, and we can go through and define a different derivative method with a bunch of here very explicit first set of first-order differential equations, where your position derivative, which is your velocity, And then your velocity derivative, which is your net thrust over mass, and these are the exact same ones to look at a trajectory in x, y, or you could call it xz space for a launch. So the relationship then can be, go through and do a different simulation. In this case, this is solving for the power loading such that the airplane goes to a minimum height of 3 feet. So I can go through and run that and get, we're launching at 6 feet of altitude at a velocity of 30 feet per second. Go through and solve the power loading such that the overall dip goes no lower than 3 feet, that was an arbitrary choice on my part, and in that case the power loading here is 22.7 watts per pound, which is a 10-pound aircraft, 227 watts is necessary. So a relatively straightforward model. We can go through and plug a bunch of different numbers into that. Rather than do it once, I wanted to create a relationship. So went through and created a different set, defined a minimum and maximum for each of the variables, went and ran about 1,008 different points, and from that created a model. We can see graphically here, and what we have is a series of sensitivities. Basically, each of these are partial derivatives with respect to that particular variable. So we have the wing loading in PSF, and then the CL during the launch, which I called CL max. It doesn't have to be, and you could be less than CL max, but it definitely couldn't be more than CL max. Aspect ratio, parasite drag, Oswald's efficiency, the propeller pitch to diameter ratio. If you have a lower pitched prop, you get more static thrust, which helps low speed, and a higher pitched prop will have higher or more thrust at a higher speed. And then the launch velocity, which I call V-throw here. And what you see is essentially your wing loading is extremely important. A high wing loading massively increases your power. And what's happening in terms of your launch speed is your required launch speed for a minimum level of power. Basically, we have this kind of threshold effect where if you throw too slow, you start needing more and more power very, very quickly. And so a very weak launch hurts you a lot. And then that's pretty visible here. You see that the power required is shooting up drastically. And so if you have a very weak throw, where you can compensate with a higher CL max and a lower wing loading, although there comes a point where that starts to not actually help. And that's because it's increasing your dimensional drag. And so it turns out aspect ratio, CD0, E, and even the propeller pitch diameter, these are relatively flat. And your launch is dominated by this velocity, CO max, and wing loading, which is not entirely surprising. And then we have this kind of threshold effect. It doesn't go below a certain level. Right, so in this case, what I fit was a neural network. You don't need to understand the technical details in terms of what that means. Don't expect that, and just an equation. It's a very large equation. But what it is a weighted sum of a nonlinear transform, in this case the hyperbolic tangent function, of a weighted sum of the different parameters here. So these are just linear, linearly combined. But you get a nonlinear model because I knew the output would be nonlinear. You don't need to understand all those details. But I can take that and paste this enormous equation, which if I look at it here, it's just a big equation that I linked to a bunch of parameters, and I can go through and change those and then see what the resulting power loading would be. Now, rather than do that, I instead integrated it into a constraint sizing spreadsheet. So this is similar to what we had before with the constraint sizing spreadsheet. I got rid of the variables that I didn't account for. I didn't account for the density, which matters mostly in terms of thrust, and I could have improved the model in that way, but I didn't. So now we have just CO max and basically your launch velocity. And we get a relationship here, which you can see is 6 meters per second. It takes a lot more power. It seems to dominate relative to other things. If I increase, this is 20 feet per second to 30 feet per second, it drops, and now it's very low. So if you get a good launch, if you get a very strong throw, or you have some free velocity in the form of wind, it's very easy to launch the aircraft. If you throw very weakly, it's extremely difficult. All right, so 30 feet per second is really difficult to actually launch the plane that fast. So you can get essentially, the airplane is fine. It launches very easily at 30 feet per second. You increase it to 20, or you decrease it from 30 down to 26 feet per second, and suddenly it doesn't actually launch. And we can see that. I'm going to do some examples here. At a fixed power, I'll just comment out the solver, which is a very horrible solver, but again, I made this very quickly. And what you see here is the vertical location starting at 6 feet. It dips a little bit. It only dips a total of 6 inches over time, which is the x-axis. And that's at 30 feet per second. But if I go to 26, it's hitting the ground, right? 0 is the ground. You can imagine the ground. So your airplane can be extremely sensitive to this hand launch. So that's something to keep in mind here. And then a way to model that is inside of this spreadsheet, which I added to the lab material back here as the electric HL. So you guys have access to that if you want to look at this relationship and plug in your own numbers and see what that looks like. The other factor is when reviewing these, it turns out this was adapted from a student who'd made some corrections, and adding this English second axis for the power loading was actually incorrect. The unit conversion was wrong. So the conversion was based on if this had been watts per kilogram instead of watts per Newton. So I extended the graph range here and then also corrected this side. This side on the previous one is off by a factor of 2. Because this is just a display of alternate units and it's not tied to the calculations. So that's something to keep in mind here, that there was this mistake that I'd not caught before. But yeah, if you were looking at the watts per pound side previously, you're going to have to double that number. So that's been corrected in this one. So here, it's just all the stuff is hand launch, and then this is all the giant relationship, everything tied in. And these are all just linked. And you can change the pitch diameter. It turns out that doesn't matter very much. You can say, oh, I've increased by a very small amount. But the hand launch here is very important. This is not some sort of perfect simulation. I assumed things that aren't necessarily true. Right? We don't actually fly at CL max, or at necessarily even a fixed CL. But it at least gives us a starting point. I also assumed the successful launch, or the definition of a successful launch, is getting within 3 feet of the ground but not hitting it. And that's also an assumption. Could make different assumptions. I don't think it'd make a huge difference in terms of this curve, what it looks like, but you get some idea now in terms of the required electrical input power. So in this case, right, if we have a fairly weak throw, 20 feet per second, which is not unreasonable, and we have our wing loading here, if we pick this point, our wing loading is around 1.4 PSF, and then we're going to need something like 1.2 kilowatts, 1,200 watts of electrical input power in order to get a successful hand launch. Whereas if we get a smaller wing, that could go down to, maybe down here. This is a very large wing at this point, but it's not impossible. It would go down to 700 watts. But so keep this in mind. We're extremely sensitive to the hand launch. And I would strongly discourage teams from picking propulsion systems that are too weak. You can run into problems very, very quickly. And if you assume I can throw really, really hard, and suddenly it doesn't really matter, the hand launch doesn't matter. But if you have one weak throw, your airplane is going to hit the ground. And see, that sensitivity is very, very strong. And if you get even weaker, now you need ridiculous amounts of power. So that also goes in terms of your requirements on the fuselage. You need to make sure that it can be hand launched hard, but you don't, from a requirement standpoint. If it requires some sort of epic hand launch, what are the chances that everyone launching your plane is going to give you an epic hand launch? It's probably not that high. So you may want to bias yourself a little bit lower on the wing loading side and a little higher on the power to give yourself additional margin for this hand launch, perhaps relative to maybe some of the points that teams have been looking at so far. So any questions in terms of this model? Like, you don't have to understand all of the steps, especially the neural network part. But that's ultimately just an equation being replaced in here with the other previous equation. It's just a much more complicated form. Okay.
Thanks, Carl. That seems really useful. I know my team needs to look at their constraint diagram and hand launch based on that.
I'm concerned that a lot of teams might undersize their propulsion system. In the past, we've just kind of encouraged them to oversize, and hopefully this gives a little bit more quantitative justification of why to oversize the propulsion.
Yeah, that's great. Okay, well, thanks, Carl, John, or Dr. Sullivan and Dr. Mako for helping us out this morning and giving us some good instruction. We'll look forward to having everybody here Monday morning, and we'll continue. Dr. Sullivan will be presenting some information to us about planning for testing and verification and validation. So have a great weekend, and we'll see you Monday.